This video is an introduction to organic chemistry. Essentially, organic chemistry is the study of molecules containing carbon. So what makes carbon so special? Essentially, there is a lot of carbon molecules. There are more carbon compounds known than all the compounds of all the other elements put together. Since there is such a wide variety of carbon-based molecules, there is a large variety of chemical processes studied in organic chemistry. We're going to look at a few examples just now. Here you can see the biological processes that allow life to exist via the production of energy. These processes include photosynthesis in plants and cellular respiration in plants and animals. So you can see carbon dioxide, glucose, and ATP are molecules involved in these processes, and these molecules all contain carbon. Therefore, these processes are organic processes, as are most of the biological processes we can study. Over here is a small segment of DNA, which contains carbon. So DNA is an organic molecule, and it is the code or the molecule that codes for most forms of life. Fuels are organic molecules. So this is isobutane, which is a molecule in petroleum. Essentially, any combustion reaction of fuels or production of fuels is an organic process. This is a small component of the carbon cycle where carbon moves through aquatic life, is reduced to organic waste, is then decomposed into nutrients and carbon dioxide and either turned into sediment or recycled back through or released into the atmosphere. So the movement of carbon around different life forms is an organic process. Synthetic materials such as nylon are organic materials, as are most domestic and industrial products like paints and detergents. What I'm trying to explain here is that carbon is in a lot of different processes. So organic chemistry is quite a large topic that is involved in a lot of different branches of chemistry. Here's an overview of what we will study in organic chemistry. I'm not going to read through these, but you're more than welcome to pause the video and have a read through on your own. We're going to start by looking at hydrocarbons, which are the most simple organic molecules. Before we can talk about hydrocarbons, we need to look at how carbon bonds. So carbon is a nonmetal that forms 4 strong covalent bonds with other carbon atoms or with other elements, in particular hydrogen. And we can look at methane as an example. So methane has the formula CH4 and it forms a tetrahedral structure with a bond angle of 109.5 degrees. So since atoms arrange themselves in predictable ways to reduce electron repulsion, which is why we've got a tetrahedral structure here with methane, we can use this knowledge to predict the arrangement of organic molecules and establish patterns. So in hydrocarbons, which are the simplest organic molecules, we only have carbon and hydrogen. And because we know that carbon forms 4 bonds, a tetrahedral bond structure, these molecules make long chains, and we can predict how many hydrogens will bond around each of the carbons. Before we can look at that, we need to think about how we can represent organic molecules. I'm going to do that with an example, and that's going to be hexane. The simplest way we can represent organic molecules is with their molecular formula. So for hexane, that is C6H14. Now it's nice and simple, but it doesn't really tell us anything about the structure of hexane. So what else can we do? We can represent hexane with the Lewis formula or the structural formula, and that shows all of the bonds involved in that molecule. Now, that does give us a lot more information about the structure, but once the molecules get bigger and more complex, that's going to take 1, a long time to draw, and 2, sometimes it overcomplicates the molecule and it doesn't really show accurately the information we're looking for. So how could we simplify the structural formula? Well, we could use the condensed structural formula. So that's where we know that carbon forms 4 bonds, so we can just write each of the small sections, how many hydrogens are bonded to each carbon, and a chemist can look at that and know that that represents the Lewis structure in example 2. An even further simplified representation is the skeletal formula, where we do a sort of zigzag line, and each turning point represents a carbon atom, and the hydrogens around the carbon are implicit. So we know that carbon makes 4 bonds, so we know how many hydrogens are going to be around each of the carbons. Now, the skeletal formula is most useful when we're drawing very large, very complex molecules, and we'll look at that more later on. So, to talk about hydrocarbons, we first need to identify this term homologous series. Organic compounds are classified into families of compounds known as homologous series. The members of each series possess certain features that are common, and in many series, the common feature is the presence of a functional group. Let's start by looking at the simplest homologous series. So the alkanes series or family contain hydrocarbons where all of the carbons are bonded by single covalent bonds. Only single bonds, no double, no triple, only single. So 2 examples here are methane and butane, with the formula CH4 and C4H10 respectively. Now, because we know that carbon bonds with 4 other atoms around it, and we know how many carbons are going to be in each of these molecules, we can predict the formula that the molecule will have. So the general formula for an alkane is CnH2n plus 2, where N represents the number of carbon atoms. We can do a similar thing with the next 2 examples of homologous series. So the first one is the alkenes family. Alkenes have at least 1 double bond between 2 carbon atoms. The examples here are ethene and butene, with the formulas C2H4 and C4H8. Finally, we've got the alkynes, which have at least 1 triple bond between 2 carbon atoms, and the 2 examples here are ethyne and butane, with the structural formula C2H2 and C4H6. So you can see as we gain more bonds, so moving from single to double to triple bonds, we have slightly less hydrogens, and that's because, again, carbon can only form 4 bonds. So we can deduce the formula or the general formula for these 2 homologous series again. So we've got the general formula for alkenes, which is CnH2n, and the general formula for alkynes is CnH2n minus 2. Finally, the nomenclature for hydrocarbons involve 2 components: the root word, which refers to the number of carbons, and the suffix, which refers to the homologous series or the family. And I've got a table here that shows the root word and the number of carbons it correlates to. So 1 for meth, 2 for eth, 3 for prop, 4 for but, etc. So a couple of examples of naming. So nomenclature means the way that we name something. So if we have C4H8, the 4 tells us that we've got 4 carbon atoms. So we can see over here the root word is going to be but. And now we just need to figure out whether it's an alkane, an alkene, or an alkyne. So using the general formula, I can see I've got twice as many hydrogens as I have carbons. So it's going to be an alkene. So the nomenclature here will be butene. A second example, we have C7H12. So 7 shows us that it's going to have the root word hept. And now looking at the general formula, twice the number of carbons will be 14. And if we subtract 2, we'll get this number here, 12. So that's the general formula for an alkyne. So the nomenclature for this example will be heptyne. And this is the general formula that I used to determine that it was an alkyne.